Okay, right. So here's where we were. Yeah, let's look at this function right here from R2 to R2. I claim that this is a linear transformation, and that's something you can just brute force check, right? You can just check it satisfies the conditions. So furthermore, I claim that this is a rotation. So like I was saying before I realized it was break time, it doesn't look like a rotation. You think rotation, you think curves. You know, things are curving in a way, and shouldn't there be an angle in here or something? And shouldn't there be a bending? Shouldn't there be like it seems like there should be a square root, maybe something like that. But this is a rotation, and it's not hard to see that this is a rotation because you can look and see exactly where the standard basis vectors go. E1, plug in 1 0 into there, and you can see the output is 0 1. Likewise, plug in 0 1, and you can see the output is negative 1 0. So green to green, blue to blue, those two vectors got rotated. And then furthermore, notice that all linear combinations represented by these rectangles go to rectangles that look like this. And so you can just look and see that in the same way that that E1 rotated 90 degrees and E2 rotated 90 degrees, so did the arbitrary vector x rotate 90 degrees. Every vector in the plane gets rotated 90 degrees counterclockwise around the origin by this function. So it's a rotation. That's kind of neat. It turns out this generalizes. So in general, if you want to talk about a rotation by any angle theta, I claim that rotations are linear transformations. And here's the way to see it. Let's suppose you want to rotate every vector in the plane counterclockwise by that angle theta right there. First I want to argue that rotation is linear. Arbitrary rotation by some angle theta in the plane around the origin is linear. Here, let me not get ahead of myself. So this vector rotates to that. This vector rotates to that. A linear combination, arbitrary linear combination. Let's see here. Let me do it about like this. There's an arbitrary linear combination of the inputs. Okay, artistic challenge. Here is the same arbitrary linear combination of the outputs. And notice I rotated E1 and E2 the same amount, so this is a right angle. That means this is a rectangle. These lengths are the same, those lengths are the same. These are the same rectangle, just rotated, right? So if I look at this linear combination of the inputs and then rotate it, whereas, on the other hand, if I took those inputs, rotated, and then took that linear combination, I'm going to end up at the same point either way. In other words, the whole rectangle, the whole parallelogram that represents the linear combination, that whole parallelogram rotates. And take your pick, how do you want to do the linear combinations? Either way, you're going to end up at that same place. So, by virtue of the fact that rotations kind of preserve parallelograms, rotations are linear transformations. Okay, so that's the first observation I wanted to make. The next observation I want to make is that once you know that that we're talking about a linear transformation, all I have to do is understand the images of the standard basis vectors. And remember, we have this theorem: if you understand the images of the standard basis vectors, you're good. You know everything else just by the linear combinations. And here's easy calculation here. the rotation of E1, that's just cosine theta sine theta. It's a little trig triangle. Yeah. So there's the rotation of E. That's the image of E1. Likewise, image of E2, you're going to look at this different triangle over here. Different ways to think about that triangle. One way you can think about that triangle is think about the sides and then think, okay, well, yeah, but I'm over in the second quadrant, and therefore I know that the x-coordinate has to be negative. An easy way to kind of bypass that is to notice that if this angle is theta, then this angle is theta plus pi over 2. And you can just talk about cosine and sine of this red angle, theta plus pi over 2. According to that vector, cosine and sine of theta plus pi over 2. And then remember all those trig identities that I will remind you again are really handy to know. The various trig identities, trig symmetries, you just got to know how those work. And that recovers for you this as the rotation of E2. Once you have those identified, it's all downhill from there. Well, let me just do it like this. X is a linear combination of E1 and E2 with its coordinates. We know R of E1 and R of E2 from up here. Multiply, collect terms, etc. And there's your general formula for rotating vectors in the plane counterclockwise by an angle theta. It's a general formula. This is really nice. I mean, this is powerful. Think about the alternative. I mean, if I were to ask you in general to take, let's take this vector there, with some random coordinates, and to rotate it, 26 degrees. How would you find that angle? How would you find that vector? Well, this is being a weird vector. I'd have to do some trig to figure out what that angle is. I might have inverse trig. There'd be a bunch of work to do to figure out what this vector is. Right? And you could bypass all of that with taking advantage of the fact that this rotation process is a linear transformation and rewriting the problem effectively as an easy question. All right. Okay, so those are linear transformations. We're going to move on now. There's one more example that I'm going to let y'all read on your own. I want to move on now to matrices. I think a lot of y'all have seen matrices before. I want to show you some things about matrices that I think you've probably not seen. One of the big takeaways I want you to get from this is motivation for why are matrix operations what they are. Okay, so first, a definition. Here's a linear transformation. Recall, we just got through noting that if you have a linear transformation, and we proved directly that this was a linear transformation, that is entirely characterized by the images of the standard basis vector. So all the information that's in this explicit formula for this function, all of that information is encoded in the fact that, well, I know TV1, TV2, and I know that it's linear. So these two data and linearity allow you to reproduce all of this. All right. So this allows us to make a shorthand, a very nice shorthand, and that is this, which is actually more compact. This is arguably less compact than what we wrote down in the first place, but this is clearly more compact than the original formula we had for the linear transformation. And the idea of the notation is this. First of all, y'all have seen matrices before, right? So I'm going to define a matrix to be just an array of numbers like this. And so what I'm going to define is that when you see a matrix, you should understand, it should be implicit, I'll say, that this is a shorthand notation representing a linear transformation. The way the shorthand works is that the first column will always be the image of the first standard basis vector, and the second column will always be the image of the second standard basis vector. And so all of the information in the original formula is implicit in what I've written down here, right? The columns tell you the standard basis images. The fact that it's a matrix tells you that it represents a linear transformation, and therefore you know linearity is part of what this function is, and therefore you have all this information. Okay. All right, so very handy notation. Now, why are matrices important? Well, there's a long list of reasons that matrices are important. We're going to do some really nice things with them here in Math 212, and Math 216 will do more, those of you who take Math 216. Just, by the way, as a reminder for me, how many of y'all are engineering majors? Great, most, not all, but lots of y'all are. Great. See you in the fall. Okay. So here's our definition. The matrix representing a linear transformation is a matrix where the columns are the images of the standard basis vectors. So that's the convention. The columns are the images of the standard basis vectors. Make sure to memorize that. I mean, that's extremely fundamental in how we're going to understand matrices. Okay. So let me not dwell. Columns are the images of the standard basis vectors. Okay. So, for example, let's look at, here's a linear transformation. How would I shorthand this linear transformation as a matrix? Well, I can compute one at a time. There's the image of the first standard basis vector. There's the image of the second. There's the image of the third. Now, that's just plugging in, right? I mean, I'm just plugging into that function, 1, 0, 0, 0, 1, 0, etc. And once I know those become the columns. And this, then, is my matrix shorthand to represent that linear transformation. Everybody on board? Writing it backwards. Suppose I have a matrix given to me. What linear transformation does this represent? How do I unfold the linear transformation out of this? Okay, well, that being a matrix, I know that the columns are the images of the standard basis vector. So I can just read straight off of there T of E1, T of E2, T of E3. And I further know that if I know T of E1 and T of E2 and T of E3, then linearity allows me to understand the linear transformation. Right? I can evaluate T of X by looking at the appropriate linear combination of those images, which then recovers that formula. So you can move back and forth pretty seamlessly between matrix shorthand and full-on, full representation of the function. Okay. So now, I think a lot of y'all have seen matrix operations defined in high school classes. And so I just want to get a quick show of hands. How many people have seen the formula for how to multiply a matrix times a vector? Quick show of hands. Oh, very few. Okay, this is actually good news. I'm glad. Here's my complaint that I have for the way this sort of thing is presented in high school. Certainly I have this complaint about how it's presented in my high school. I suppose there was really no alternative. It's another one of those situations where, like with the equation of a line, remember how I was griping about the fact that they don't tell me the A comma B means something. Why didn't they tell me that, right? Well, it's because they can't do dot products. Okay. And likewise, I confess, okay, sure, they can't, in a high school context, spend a bunch of time talking about linear transformations. But it remains, though, I think, sad, however unavoidable it might be, that students get told how to multiply a matrix times a vector, but don't get given any reason why it should be And why would that formula be the formula? They just told me when I was in high school, they just told me, here's how you multiply a matrix times a vector. And I was thinking, because this is, I mean, why? What's the context for this? Are we just making stuff up here, or why did we do this? It seems very, very arbitrary. I never got satisfaction until I took a linear algebra course. Okay, so here's the case I'm going to make for y'all. And again, if you haven't seen matrix vector multiplication before, cool. I don't have to unfold anything. Keep in mind that what a matrix is a shorthand representing a linear transformation. So if we want to ask, what does a matrix do to a vector? Well, I mean, what all a matrix is? A matrix is just a linear transformation. It's a shorthand. What the matrix does to the vector had better be the same as what the linear transformation does to the vector. It's just a shorthand representing that same thing. These are supposed to be the same thing. So it's extremely plausible that, when we define matrix times vector, shouldn't the answer be whatever that corresponding linear transformation does to that vector? I mean, if it weren't, that would be kooky. I mean, it'd be insane for this to not be the case. So this is going to be our motivating interpretation. This is what I call interpretation 0 of matrix vector multiplication. Matrix vector products are defined by this. The matrix does to the vector whatever it is that its linear transformation does to that vector. Okay. And then you can trace out what that actually looks like in terms of arithmetic by just using linearity. So keep in mind these columns are the images of the standard basis vectors. That's our convention for what a matrix is. So I'm going to give those names. I'm going to call them A1 through AN. And look, T of X, by linearity, T of X is this. These columns are what those images are. And so our formula, if you want to multiply matrix times a vector, it sort of has to be this. If you want matrix vector multiplication to be consistent with the fact that matrices represent linear transformations, that means that what the linear transformation is doing is indicated by these columns being the images of the standard basis vectors, and linearity forces it upon you that this is your formula for how to multiply a matrix times a vector. So nice result. If you want to multiply a matrix times a vector, you're going to take a linear combination of the columns of the matrix where you use the coordinates of the vector as the coefficients in that linear combination. We have no choice. We have no reasonable choice otherwise. All right. So you'll notice that's the formula I have written down here. So the matrix has columns, A1 through AN. The vector has coordinates, X1 through XN, and the product, take a linear combination of those columns using the coordinates as coefficients. Okay. Now, those of you who have seen matrix vector multiplication might not have seen this version of this formula. Now, let me segue into the version that y'all have seen, for those of you who have seen this. Notice this interprets matrix vector product as a vector, as a linear combination of other vectors. It interprets this operation with vector algebra, right? Here's an equivalent definition And the equivalent definition is going to come about by asking, okay, well, what are the individual coordinates of this matrix vector product? If I want to understand that product one coordinate at a time, not from vector operations, but with individual coordinates, how would I compute those individual coordinates? The observation to make here, this is really just a kind of a clever observation, that this linear combination, if you want to compute just one coordinate of it, let's say the first coordinate, for example, how would you compute the first coordinate of a linear combination? Well, you would just take that linear combination of just the corresponding first coordinates. Right? You would take, instead of taking all of these vectors, you'd look just at those first coordinates, and you'd take this linear combination of just those first coordinates. And there's a silly little observation to make, but a linear combination of just a list of numbers, this times that, plus that times that, plus that times that, etc. It's a dot product. So it is. This times that is that dot product. So this is the formula that they showed me when I was in high school. It was the very first formula. Definition of a matrix times a vector was to take the rows individually, one at a time, look at the rows of the matrix, and then you take the vector that you're multiplying it by, and one at a time you dot your vector times the individual rows of that matrix. And those individual dot products make the coordinate of your product vector. Now, for those of you who have seen matrix vector multiplication before, how many of you, this was the formula that you saw? Okay, right. Exactly. Okay, so this is the way they always, they almost always teach it in high schools. So these are equivalent definitions, right? Neither one is wrong. You can think of a matrix vector product. Let me get out of that color. You can think of a matrix vector product as in terms of linear combinations, or you can think of a matrix vector product in terms of dot products. It's linear combinations of the columns of the matrix. It is dot products with the rows of the matrix. You got to keep that straight. That's important, right? You can't. It's not a mix and match situation. So just a little perspective for y'all. A little, a spoiler, let's call it. Between these two, which one is most useful? This one, linear combinations, right? The reason that they show you this formula in high school is because they ask of you very simple things in high school classes where they talk about matrices. They say, all right, well, here's a matrix, here's a vector, let's multiply them. And they basically have you doing a bunch of arithmetic. And when you're doing arithmetic, I will confess, this dot product formula, very handy for arithmetic. Very convenient. You can just, boom, boom, boom. The arithmetic lays out very nicely on the page. You can just write down answers. From an arithmetic point of view, this is super. If, however, you need to do thoughtful algebra of matrix operations, matrix vector products, and relating ideas to other ideas, making significant discussions. This computational point of view is not as useful. I mean, every so often, sometimes, yes, it's dot products are a significant idea. Sometimes this is exactly what you need. Far more often, understanding that this product has this linear relationship with the column vectors, far more often, this is the useful tool. Right? So, you just got to keep in mind that, in a high school context, you have very different goals. And now that we are no longer in a high school context, make sure to draw your attention to this one more so than this one. Okay. Alrighty. And I think I have some examples here. Yeah, so let's take a linear combinations point of view. How do I multiply? Let's see here. I want to multiply this vector times this matrix. Notice this matrix has these 3 columns, and I'm going to compute this product by taking those 3 columns, doing a linear combination with these 3 coordinates of my vector, and that linear combination, you can crank it out, and that product is this. That's just arithmetic. By comparison, now this is just the other option. You can compute that same product by taking a bunch of dot products. So here's the vector that we're multiplying by. We dot that same vector, you'll notice. Dot that same vector individually with the rows. One at a time. Right? And all of these dot products will give you, you notice it's the same answer. So, well, there are 2 different ways of doing the same thing. That's what they look like. Okay, how do you add 2 matrices? Next question. Pause. Why would we add 2 matrices? We're just making stuff up here. Why are we adding matrix? What's a matrix again? Oh yeah, okay, so a matrix represents a linear transformation. We're really thinking about linear transformation. So if I'm going to add 2 matrices, that should be shorthand for I'm adding the 2 linear transformations. Well, how do you add linear transformations? Well, that's a pretty straightforward matter. Adding linear transformations, don't forget linear transformations are functions. Adding functions is something we've been doing for a long time. Right? The way you add 2 functions is by adding their output values. So when we add 2 matrices, we better make sure that the formula that we write down for how to add 2 matrices will actually accomplish this. We had better effectively be adding the underlying linear transformations. Nothing else would make sense. Okay. Okay, so that has corresponding consequences. So I'm going to compute now what the sum of 2 matrices had kind of better be. Specifically, I'm going to compute this matrix A plus B. By the way, where did I write this down? Yeah, so I want for organizational purposes, I want T to be represented by the matrix A. I want S, the linear transformation S, to be represented by the matrix B. So just make sure to recall T is represented by A, S is represented by B. And with that in mind, how do I compute A plus B? I'm going to do it 1 column at a time. The columns are the images of the standard basis vectors. That's our rule, right? Remember, that's our convention for what it means to talk about a matrix. The columns are the images of the standard basis vectors. We just got through agreeing that adding 2 linear transformations had better be adding the output values. That's how you add functions. Always has been. And of course, T is represented by A. So the image of T of EJ is the jth column of the matrix A. And then likewise, S of EJ is the jth column of B, because B is the matrix that represents S. And all together then, notice our nice punchline, the way you add 2 matrices, the column, a given column of the sum has to be the sum of the individual columns of those 2 matrices. In other words, you add matrices 1 column at a time, I'm going to say. So let's see an example of this. If I want to add, this matrix plus that matrix, well, this first column is going to get added to that first column to give me the sum first column. And then you notice, but adding columns are just vectors. that means we're really just adding individual elements. So there's a really nice punchline. That plus that gives you that. You add matrices exactly the way that is, most symbolically convenient on the page. And it's a wonderful convenience. Very importantly, though, this is not why we add matrices like this. We don't add matrices because it sure is handy to do it like this. Right? We add matrices like this because this is the process of adding matrices that corresponds to adding the functions that they represent as functions. So this is what it ought to be for good reasons. How are we doing? Is everybody on board? Okay. Now where it gets a little weird is when we start talking about multiplying matrices. Now again, some of y'all might have seen a formula for how to multiply a matrix times a matrix. And if you have, I would be very surprised if you saw a really persuasive explanation of why the weird little formulas they show you in high school math classes ought to be the answer, right? As opposed to just an arbitrary, well, do it this way because I told you so, right, kind of a deal, which is what I got told. So it's going to come about from considering the following question, and that is, if you have two linear transformations, let's think about what would happen if I composed those two linear transformations. Y'all remember compositions? It means you plug, what comes out of one function then goes into the next function. Yeah? Okay. Right. So I want to ask, let's just consider this scenario. We've got a linear transformation T from Rn to Rm. And then what comes out of that, sitting in Rm, let's apply another linear transformation S from Rm to Rk. And this sort of plugging in kind of thing is called a composition, and I hope y'all remember this notation for composition. So in a Calc 1 class, you should have seen this notation as part of a discussion of the chain rule. Do y'all remember the chain rule way back when? Okay. So this notation here just means composition. And sadly, it looks backwards. It's so frustrating. It really looks backwards. It looks like, the S is on the right. How come the function's written there on the left? T is on the left in the diagram. How come it's on the right in the algebra? Y'all see the concern, right? And notice that I'm going to call it a necessary evil. This is unavoidable given certain other conventions that cannot be undone in terms of how we write functions. It's got to be this way, as it were, because look at how we actually do a composition. Very importantly, when you do a composition, the first function to act on X has to be the one that's written on the right in the algebra, but it also has to be the one that's on the left in the diagram. We make it, this is a left to right culture. Our arrows go to the right. That's how it's very deeply ingrained in how we write stuff down on a page, right? And the way we write functions, and again, this is, technically we could try to break the mold and do it differently, but planet Earth would not be happy with us for doing this. The function gets written on the left. That's how you write functions, right? So it's just got to be this way, sadly. And this is a terrible potential for oopses. I've committed this myself to great loss, where getting it backwards, seeing it in a diagrammatic context one way, and then forgetting to switch it when you write it algebraically later. So please be very, very careful about this. Make sure you understand what the conventions are and why, and be careful and don't use it. Okay. All right. So here's the thing. If this composition is going to be represented by some matrix, I don't know, let's call it C for the moment, whatever that's going to be. Well, don't forget, T is represented by A, and S is represented by B. And man, I'd be really uncomfortable if this wasn't true. Right? I mean, let's think about our algebraic future. Right? If we would like to define operations that allow us to do reasonable algebra, and associativity, whew, man, that's really convenient. More to the point, not being able to apply associativity would be crippling. Right? Well, then it just kind of has to be, unavoidably, that the matrix product B times A has to be the matrix that represents the composition of two linear transformations, S and T. So, again, circumstance kind of foists this upon us, right? We're not making a kind of arbitrary choice here. We kind of have to define a product of two matrices as being representative of a composition of linear transformations. And that's going to dictate for us what the formula for matrix multiplication has to be. This has to be whatever this says it has to be, and there's going to turn out to be some rules that do it. So here's the how that plays out. And just for notational purposes, we're going to use capital letters to represent the rows of a matrix. Just for convention. We're going to use lowercase letters to represent the columns of a matrix with a subscript. Right, very handy. And, well, here we go. This product, B times A, I'm going to compute it one column at a time. By the way, in case you're wondering, the reason we tend to focus on computing things by understanding the columns is because columns, it's a foot in the door. Columns are images of standard basis vectors, right? Understanding something by understanding its columns allows us to get a foot in the door into the algebra that allows us to actually get somewhere. So here we are again. So the column, the jth column of this product is the image of the jth standard basis vector. Composition means that. Execution of T means multiplication by A. Execution of S means multiplication by B. When I multiply a matrix times the jth standard basis vector, I get the jth column of that matrix. Recall this notation up here. Lowercase letters mean the corresponding column of that matrix. And what I've got then is, this is in fact a formula for me. A column of the product is this matrix times this vector, and don't forget I have existing formulas for what it means to multiply a matrix times a vector. Yes?
So is it just doing a vector matrix multiplication twice?
Say it one more time, I'm sorry.
Is it doing a matrix vector multiplication twice for the A times?
Yeah, that's right. So you're quite right. So we've got this into, from linear transformation algebra into matrix algebra, and this first matrix vector product is an easy one, right? And then the second one is just a second matrix vector product. Absolutely. Yeah. Okay, now let me remind you, what do we know about how to multiply a matrix times a vector? We had a couple different ways you can think about it. One way to think about this is this matrix vector product says we're going to take the columns of B, right? We're going to do something with the columns of B. We're going to take a linear combination of the columns of B, where we're going to use this vector as our coefficients. Let me say it a little bit differently. We're going to take a linear combination of the columns of the left matrix in our product, linear combination of the columns of the left matrix, where we use a column of the right matrix as our coefficients. Now let me say that again just a little bit differently. we're looking for the jth column of this product, then inside of the right matrix, we pick the jth column of that right matrix to be our coefficients. Okay, so all together then, a column of the product is a linear combination of the columns of the left matrix where I use the corresponding column of the right matrix as my coefficients. And so this is what I have down here as interpretation 1. Columns of the product, linear combinations of the columns of the left matrix, corresponding column of the right matrix as our coefficients. Everybody on board? This has got to be. So let me skip down to an arithmetic example. Suppose I want to multiply these matrices. Okay, well, this product here. Let's compute the first column. Oh, I'm sorry, color mismatch. Let's compute that first column. Where does this first column come from? Well, that first column, I'm taking a linear combination of the columns of the left matrix. You can see them right there. Columns of the left matrix, where I use the corresponding columns, the corresponding column of the right matrix as my coefficients. All right, so I'm literally going to since I'm looking at the first column of the product, I look at the first column of the right matrix. Those numbers 5 and 6 tell me how to take a linear combination of the columns of the left matrix, get that corresponding column of the product. Everybody on board? Now, here's what I think is really important about this. This wacky little formula, we didn't really have any choice, right? I mean, we kind of had to. We had to make this choice because this algebra says I have to, and this algebra relied on this motivation that, well, I really want that to be that. So unless you just want to deal with some insanely inconvenient, semi-useless algebra, you kind of have to do this. So said differently, the reason that we use this formula for matrix multiplication, and by the way, I'm going to give you different versions of this momentarily. The reason we use this formula for matrix multiplication is because that's the only reasonable way to define a multiplication that naturally connects back to linear transformations. If you want matrices to actually be interpreted as linear transformations, as we do, this being how you compose linear transformation means that this is how you have to multiply matrices. Okay. All right. Now, there's some other details that you guys can wade through on your own. Reminder that in this product, let's look at the first column of a product. And remember, that we know that first column of the product is we take the matrix and we multiply by this vector. And we also recall that there is a different way to multiply a matrix times a vector. A different way to multiply a matrix times a vector is not with linear combinations of the columns of the matrix, but with dot products with the rows of the matrix. Right. So what you have here, you can compute these individual elements in that column by doing dot products. Right? And so applying that to all the different rows, you get this other point of view on matrix multiplication. And this is just a matter of just looking at the details and seeing how everything fits together. But the other point of view you can take is that for any given entry in the product matrix, you look at the corresponding row of the left matrix and then the corresponding column, corresponding column of the right matrix, and row dot column. So it's just a different way to think of this matrix vector multiplication that gave us that point of view up there in the first place. So this is what they showed me in high school. They showed me in high school the way you multiply a matrix times another matrix is one element at a time. If you want to compute a given element, you look at the corresponding row of the left matrix, you look at the corresponding column of the right matrix, and you do a dot product. And I was just like, why? Where does this, okay, if you say so, right? But, are you just making stuff up? I was really very uncomfortable with the fact that they gave me a weird formula about rows here, but columns here, and then do dot products for no reason that's indicated at all. Very uncomfortable. So again, why is this the formula? Well, it's because this is what the formula has to be consistent with the above point of view about linear combinations, which is what it has to be consistent with the fact that these represent linear transformations. Okay. All right. So now one last observation that I'll make, and this is just a matter again of getting into the weeds and looking at it a different way. In addition to looking at linear combinations of the columns of the left matrix, alternatively, and I'll say it's surprising, but alternatively, you can understand a product by looking at linear combinations of the rows of the right matrix. If you write that down, look at the individual coordinates, what you'll find is that it reproduces these same formulas here for the individual elements. They're just dot products. So that is a kind of a third point of view that you can take on matrix-matrix multiplication. Also very useful, as it turns out. To me, personally, I think it's more fundamental to think of that we're taking linear combinations of the columns of the left matrix. But be aware it's also true we're taking linear combinations of the rows of the right matrix. So let me do a little bit of arithmetic for you all here. So we already did interpretation 1 here. We already interpreted this product by looking at the columns of the left matrix. That gave us this. Here's the dot product point of view. Across the top row, you use the top row of the left matrix. Across the bottom row, you use the bottom row of the left matrix. In the first column, you use the first column of the right matrix. In the second column, you use the second column of the right matrix. This is the dot products point of view on matrix multiplication. You can just dot out all 4 of these dot products. Nope, same answer either way. And then lastly, you can compute these matrix products one row at a time. This first row here, you can understand as coming from looking at a linear combination of these rows of the right matrix using these numbers, the corresponding row of the left matrix as your coefficients. And likewise, the second row of your product using the second row of the left matrix as your coefficients. All 3 of these give you the same answers. Ultimately, all 3 of them are kind of doing all the same arithmetic. You can even notice in here, let's just last point, real super quick. You can even notice in here that this 34, from this linear combinations of rows point of view, that 34 comes from. Well, let's see here. There it is. It's the left entry here. So it's 2 times 5 plus 4 times 6. And you can see there's the 2 and the 5 and the 4 and the 6. And you can see I'm doing that dot product. You see it right there in the arithmetic. Right, and likewise when you're doing columns. Okay, so there's several different points of view then on matrix multiplication, and that is a nice ending for today. So we've just finished 3.2. Don't forget we have a test on Wednesday. Seems too soon, doesn't it? Yeah. So anyway, test Wednesday, and the fair game material is everything that we've concluded that we finished now. So we have now, by the way, we are done with chapter 3. There's the exercises. So tomorrow we will be proceeding with chapter 4.
Stuff we do tomorrow is not
Correct. The stuff that we do tomorrow in chapter 4 is not fair game for the midterm. Chapters 1, 2, and 3 are all fair game for the midterm on Wednesday. See you later, y'all.